Thanks, Facebook. Yeah, how's it going? We can do this. Is this somewhat interesting or somewhat overwhelming or both, maybe? It's a lot to think about. Let's do it this way. Look, when you have a multivariate model, the first step is fit. It's just, and then all of a sudden there's all sorts of ways of fit. What you're trying to do with model fit is, again, just keep the big picture in mind. I'm trying to make my model, what the model says the data should look like the data really actually looks. And yes, it is a different way of thinking. You have to stop yourself after you run the analysis before you look at the results and say, wait a minute, should I even believe the results? Because sometimes when you change a model to make it fit, sometimes the results change significantly, sometimes. So yes, it is. The number of, the volume of information that comes out of the computer is definitely overwhelming. Why that's there? You want me to be real with you about model fit? I don't know if I can be real. As real as my opinion can be. You know what they say about opinions, right? That's how it works in the academic world. So I have this. I kind of have two hats. I came through social sciences as undergraduate and grad school, but I also got a degree in statistics. And the statistics world, which really kind of the statistics I learned sort of grew out of agriculture and whatnot. Their version of model fit comes from this test statistic right here. Right? If you don't fit the data, if that test statistic doesn't work, model fit doesn't happen, game over, don't ask any questions. So it simplifies it, right? Because you don't have all this other stuff that falls out. Turns out, in a lot of things we do in social science land, that first test statistic, this likelihood ratio test for our saturated model, the p-value is almost always very tiny there. Almost always. So rather than be like, well, none of our models fit, we created excuses for why they didn't fit and created new indices to sort of describe how bad our fit happens to be. So I wouldn't say that. I shouldn't say that because in the ag world, the world that I grew up in, the stat side of me, even though none of the people were in agriculture, it was sort of heavily influenced by that group. Their sample sizes are fairly tiny, right? They're talking about doing experiments on some type of animal, and they are concerned, for the most part, about not hurting too many animals and so forth. So they have a small sample size. And when you have a small sample size, it turns out this likelihood ratio test, people in the social sciences have discovered, it's very powerful. It's very easy to see a model doesn't fit if you have lots of data, and there's a small perturbation. Some small covariance is not exactly what it should be. It picks up on that and throws the whole thing out. Right? And so that's why you start to see these other numbers. Basically, these are trying to describe not just the absoluteness of statistical significance, but sort of a by degree of freedom, or sort of in comparison to these other models, how bad is it? Right? So it's sort of degrees of misfit that you see in these other statistics. And that's where they come from. So yes, model fit it complicates things a lot. It makes a lot of numbers come out, but really there's a handful of things extra to think about. We haven't even gotten to talk about results, but sure enough, my slides on results are like 2 pages long because the same results, the same interpretation that we had before applies here for each of the variables in the analysis. So the good news is a lot of that stuff you've already learned is you're going to benefit from here, and what I've tried to do is isolate the new part of multivariate models, particularly the model fit, this lecture, being somewhat separate. But I hope that helps break it down a little bit, right? So when we get to mixed models, when we get to the next section where we're doing the same thing but from a different paradigm, it really grew from the stat modeling world, you're not going to see any of this model fit output. It's all going away. It's going to be very hard. The way they look at fit, again, is very different from that in those disciplines, and mainly because most of the times their modal data analysis when they were building these methods had a lot fewer observations, at least what I'm going to claim, than what you see from our models in the social sciences. And why do I say models in the social sciences? This type of multivariate regression isn't really one of the ones I'm talking about. Where you see most of this model fit growing out of is factor analysis and structural equation modeling. Because in those models, you often find degrees of freedom that have numbers that are very large. If you've got a 30-item test, if you've got a 30-item questionnaire, and you think you're measuring one thing, you're going to have something like 200 and some odd degrees of freedom to test that. And the degrees of freedom are there basically saying how many, like you've got this big covariance matrix that could have all these covariances in, and you're trying to fit a model that has this smaller set. So you can imagine there's lots more places for it to go wrong when you have those big degrees of freedom, and that's what you start to see in the social sciences, educational sciences as well. So I hope that helps with the perspective. So I have a hard time. I try to wear both hats, and I try doing it whatever. I know that the stat side of me really likes this hypothesis test, but then I also know that's a very literal thing. You may be rejecting a null hypothesis for a very small effect size, and I think that's what the social science aspect of model fit is. You want to make sure the other numbers are trying to quantify the effect or how big you're not fitting your model with. So. Okay. So once again, we fit a model now that has perfect fit. Can we take a look at what the model implied covariance matrix is and compare that with what the data look like? You want to do that? You can imagine what this looks like. Here's what the model implied covariance looks like. And I didn't put it in here, but let me just grab this, what the data implied covariance matrix happens to be. Actually, I put it up above, so that seems to work. But if I did this. So now, if I look at these covariance matrices, I should see the identical numbers in both. And that's what happens in a saturated model. When you fit a model that's equivalent to the saturated model, it means that your model is going to reproduce the data's, here's your model, this is what's coming from your model, and this is what's in the data. So what you're saying is that you're reproducing what the data's covariance is exactly in a saturated model, or a model that has as many parameters as the saturated model. Cool? So when it reproduces exactly, you can imagine what's going to happen to the residual matrix. You should see this, right? Zeros, because one minus the other should leave 0. That's perfect fit. That's a saturated model for you right there, right? So when you see zeros, that's what's driving all the numbers in the table and everything else that happens. So, how are we doing? Okay. Yes, please.
I've got the picture now. You said that when we're using the fitted function, what we're getting is what we get from our model, and then the inspect function is the data.
Yes, that's correct. Sorry about that. I should have gone more into that because I rarely see people just looking at the data, but I'm trying to do it for teaching purposes. But yes, the inspect function, when you tell it what equals sampstat.h1, gives you what the data says. And then fitted really tells you what the model thinks the data should be. So yes, it's sort of a ambiguous titles that both of those go under. I'm sorry about that. Thank you for asking. I appreciate it. This is why questions are great, by the way, because I'm rapidly becoming senile, I feel like. You ever had that feeling where you're trying to remember all the things you want to say, and it's like, because it's a complicated topic, it just makes it harder, I feel like. Now I'm making an excuse for myself. Let me just go with that. I'm young enough not to be senile yet, unless there's some biological problem I have. Nothing evident that says that's the case. It's really hard to talk about this. It's really hard to learn about this. I apologize for not being complete as much, but this is where your questions help. So please do ask them if you have them. I hope it's good for you. But back to the point, though, right? So we have this model. We fit the analysis. We saw 0 degrees of freedom. So what we would expect to find is that our parameters match the saturated model. Next, anything else we would find would also do the same thing. But let's go interpret the results, shall we? This means, remember, if model fit's your gateway to looking at the numbers, this means we should look at the numbers. Do some interpretation. Okay, here we go. The part of the model that most people want to talk about, and rightly so, is this section that comes out under regressions. So where do I get these numbers from? If I go back to R, this is the summary function, just like you use for the LM or for CLM or whatever else. Summary, once you pass all the model fit stuff, you get into the numbers themselves, the betas and so forth. And these are the regression weights. So now let's take a look at those. This first thing is the regression, predicting performance on a math test. The first effect is female. This is the main effect of female. Is it a conditional main effect? Or better yet, is it a simple main effect or an unconditional main effect? It's simple because female shows up in the interaction. So this is for a person. So for people who have 10 credit hours of math, the difference between male and female in number of points correct on performance is 0.51. This is exactly the same interpretation that you would have of that simple effect if all we had was a regression with performance in it. Same numbers, same everything, right? We also can tell the p-value here is sort of telling us that when CC10 equals 0, or when someone has 10 credit hours of math, there is no significant difference between men and women, or females and males, in the number of questions answered correctly on that performance test. Right? So now let's go down to that same effect for usefulness. And we want to try to interpret it. First of all, simple main effect or unconditional main effect? Simple main effect again. And the way we tell it simple is still for that prediction of that one dependent variable, right? So you look at that, where you see use tilde, that means these are all applying to usefulness, the prediction of usefulness. So if there's an interaction here that involves that variable, then yes, it's simple. Right? But it's possible that on one of these it's simple, and on the other one it's unconditional, right? It depends on what we specify in our model for each of those. But here it's a simple main effect, yes. Someone want to try interpreting what this value means? I'll help. For people who have 10 college credit hours, bingo. Females believe math is 1.96 whatever points more useful than males when both those people have 10 credit hours of college math experience. But we'll also see that the p-value indicates that that's not a significant difference between the two sexes. There's really no sex difference for 10 credit hours. So this sound familiar to you? The same thing would happen with the CC variable. So this, when now this is a simple main effect when female equals 0. So for men, this tells you that for every one additional credit hour of math in college, we would expect men's performance scores to go up 0.096, right? Which is significantly different from 0, but a tenth of a point. That's how much more we're talking about, right? That's how much 1 credit hour of math in college gets you for this example. Likewise, for usefulness, for men, for every 1 credit hour of college math, the usefulness score goes up 0.192, which was not significant. Now that interaction can be used to go and figure out, for instance, the slope difference between men and women. Right? We can go form the slope for men, we can form the slope for women, and that's actually what I'm doing in these values right here. So if I wanted to figure out what was the slope of CC for women, so what is the slope of credit hours predicting performance for women, right? Female, I guess I should say. Slope for female for CC10. Well, how would we figure that out? We'd have to turn this interaction back on, so female equals 1 here, so it would be the sum of PCC plus PFCC, these two labels. And that's that last part of this Lavon syntax that helps me create a brand new parameter. Once I provide a label for that beta, right? So again, I enclose the label in parentheses. I don't know if that's needed or not. I just try to do that to help offset it in my own mind. That says if I go and use that label somewhere else, I'm going to take that number of that beta and put it there. And for us now, what that means is we can see that PCC10 plus PERFCC, if I wanted to add those together, I could create a brand new variable that I'm going to call CC perf female, which means the slope of CC on performance for people who are female. And the way I create that variable is the syntax of colon equals. So if I put colon equals in, it allows me to make those betas add together. This is the equivalent of GLHT. Right? So now the cool thing, the thing I like about this is it's really direct, right? It's like if you can envision beta weights in front of each of these variables, which is really where they show up in the model, you can label them, and then you can just take your label and add them together, and it gives you the result. Like GLHT, you had to go and figure out which one they were in the matrix and whatever else. Now you don't need to do that, but you do have to provide the label for each, right? So similarly, if I wanted to find the slope of college credit hours for females, for usefulness now, I would need this beta weight plus this beta weight. And that's what I do in this last term here. And when I do that, in the Lavon output, at the very bottom, it creates a section called Define Parameters. The defined parameters indicate which variables are significant, right? Or it tells you the parameter estimate. This is the slope. For instance, this right here is the slope for of college credit hours predicting performance for females. 0.187. It's significantly different from 0. This next term is the slope of college credit hours predicting usefulness for females. If you wanted to, you could compare the slope for men and women as well. You want to do that real quick? All right. So I have here, let's do this. Diff F or M diff CC for performance. So this is going to be the difference in the slope of CC for performance. What was the slope for men? It was just this simple main effect. That's that beta by itself, right? So I take PCC and I subtract off, and in parentheses, I put the slope for female, but I put the labels in. Right there. All right, now you can tell, I mean, I have a +1 here and a -1 there, right? It would just be the interactions, the difference. This is, remember the betas? This is sort of where you can see where I would draw on the board, and I'll be like, remember this beta, and this one cancels and whatnot? You can really see it cancel here, but you don't have to. I'm just going to let it, I'm going to let the computer cancel it for me, right? And when I run this analysis again, when I go to the summary, you should see the difference. -0.091. That should be equal to the interaction. Actually, well, the sign is different from the interaction because of the way I subtract. I took male minus female. The interaction is female minus male. But it gives you the same p-value. How's this sitting? So everything that we've learned at this point, while I've been drilling these interactions in, still apply. They're a little bit different to get about once you're in the program, but that's okay. I know you can solve it. The results then work for each variable of the analysis. Let me try one other thing. I want to play around with this a little bit more. Did you notice, for instance, that we see a variable here like this interaction variable? Let's take the one for usefulness. This p-value is pretty large. We don't need that parameter in the analysis. What if we were to take it out? What do you think happens? I know, don't break it, right? Let's make another model. I want to show you what happens real quick. We're going to make another model real quick here. This is going to be model 3. And model 3. And here, this is the, I'm going to take this interaction between female and college credit hours. So I'm just going to put a 0 there. And just to be consistent in my own syntax, I'm going to put 0 without the parentheses. That tells me that that beta weight's going to be fixed at 0 now, right? That also tells me that I cannot estimate this thing anymore. So I put the syntax in, change my model statement. And I really want to show you the summary here real quick. Now, in the summary, take a look. We need to look at model fit. Now we have 1 degree of freedom. That 1 degree of freedom came from us making one of the parameters equal to 0. So with us putting that parameter at 0, that's where degrees of freedom come in, right? We basically are estimating 1 less parameter than our saturated model. And we know that because the model before this had 0 degrees of freedom, and we zeroed out one of those parameters. So that means we're no longer estimating it. You get that? So we see that the p-value here is very large, which means we fit as well as the saturated model. So this is still good model fit. The numbers that you see in the tables, we want the RMSAA to be 0. It'll be less than 0.05. It's like 0. We want these to be above 0.95. Sure enough, the TLI actually can go bigger than 1, although you rarely see it. But this is one of those cases where it happens to be like that. We're so close to fitting perfectly. This is why it's happening, right? We're really close to the perfect model fit. And we look at our results, and again, our results change slightly. But I really wanted to do that because I wanted to show you the difference in the fitted, what the model thinks the matrix looks like, what the data matrix looked like, and what the residuals happen to be. So here's our fitted model matrix. This is the model matrix from the model we just ran, right? It's got numbers everywhere still. Here's what it should look like. But here's the difference between the two. And what you'll see is now there is a bigger covariance between where that interaction variable was and usefulness. That's where the biggest discrepancy is. And the reason for that is the beta weight is sort of like a covariance. It's a way of describing the relationship between those two variables. So when we put a 0 on that beta weight, it's like saying we're taking away the covariance. It's not exactly the case because there are other terms in the model that lend themselves to that covariance. But it is true. It is, actually, that's not the model. The model is right here. I just wanted to show you that a little bit more. Rather than going overboard, what I encourage you to do, I mentioned this to one of you before, but I wanted to tell you this. Watch the path analysis. If you're kind of weirded out by model fit, watch the path analysis lecture and try to play along with the numbers in the file and just start making some parameters 0 and see what happens. Put a 0 star in front of it. Because what's going to happen is you're going to start to see the model fit change when you do that. And you just sort of got to get a feel for what's happening with the analysis itself. The other thing I wanted to note is sometimes it may be the case that you might want to not make this 0, but you may want to go and let's test the hypothesis here. I don't know why I'd want to test this specific hypothesis, but let's just pretend that we want to test the hypothesis that the value of the interaction is equal across both of these models. Is that a weird one? But we can. This is the nice thing about multivariate models. Now we've got these two predictors. We can test to see if certain effects are the same across the two predictors, all in the analysis. The way we do that is we put the same label in place for both of the interactions. And what it will do is estimate those parameters, but keep them equal. It's what we call a constraint, an equality constraint. We set them equal to each other. Again, I don't know particularly why you'd want to put this constraint in, but occasionally you might say, I want to test whether or not these two effects are equal in these two variables, or if one's bigger than the other, right? Sometimes that pops up in research. In this case, it's an interaction effect, but I can do that. I can run the analysis. I can take a look at model fit, and sure enough, or the summary for this, and once again, we still see that 1 degree of freedom. Because when we set them equal to each other, we're not estimating 2 parameters, we're only estimating 1. So that's what frees up the degree of freedom that we have. We again see like spectacular model fit. This is because it's simulated data also. When you make up your data, when you fake the data, everything works. Don't do that. Don't take that to mean anything about your dissertations, please. But here what you'll see is these numbers for this interaction here on this line and here on this line are identical in that regard. So they give you both the test. So, okay, finally, last part of this before I go and talk about the homework is the idea that we might have something called a standardized parameter show up. A standardized parameter is one that removes the units from each. Why do I say that? Let's take a look. I'm going to go back to Model 2. Model 2 was before we started messing around with everything. Take a look at our effects here. Take a look at the effect of female here, predicting usefulness. The beta weight's 1.96. When you look at the beta weight for the simple main effect of college credit hours, the beta weight's 0.19. So if you look at those, you're like, hey, 1.96, there's a bigger difference for female versus male than there is for CC10. And really what's happening, though, is those beta weights, remember, the way we describe them sort of gives the clue. For every 1 unit increase in X, Y goes up however many units. Well, it turns out, when we put this multivariate model together, not every variable has the same units. What are units? Roughly translate into standard deviation, right? So what we can do is take our beta weights and remove the standard deviations from them. If we take the beta weight, so let me back up. This is what we did with covariance. Correlation, I said, was unitless. I started class with this, and sort of was foreshadowing what we're doing today. We took the covariance had units attached to it. It was units of y times units of x. In the very first example in class, it was like inches times pounds. And the way I divided off those inches and pounds was to divide by the units of x, which is the standard deviation of x, and times the standard deviation of y. And it was like in part of chemistry that's called stoichiometry. I remember we used to cancel units out and do whatever else. We're sort of doing the same thing here, leaving us with no units or a number that ranged between -1 and 1. Well, sure enough, we can do the same thing with the beta weight. The beta weight is units of y per units of x. So if we divide by the units of y, if we take the beta weight and divide it by the units of y, we've just taken the units of y out. And if we multiply by the units of x, we take the units of x out. And sure enough, what we're getting is a standardized parameter, a parameter that has the units of y being the same as all the other units of y's that are out there. So why do I say this? Because sometimes you might want to compare the relative size of the parameters. And the way to do that is to look at the standardized column. In Levon output, if you take the summary model and you add the option or the argument standardize equals true, take the summary function, add standardize equals true, you get another column. You actually get 2. Ignore std.lv. That stands for leave it alone. No, LV stands for latent variables. We have none. Those are like factors and stuff. Just ignore those right now. Just look for std.all. Yeah, and that right there represents the beta weight if we were to have had no units of y, units of x. So let's go interpret that. Let's take CC10 because we know what standard deviation of CC represents. It's sort of the, how much variation there was in CC. The way we interpret this result is instead of saying for every 1 extra unit of CC10, performance goes up by beta units. Watch, subtle difference here. For every one additional standard deviation of CC10, right? The difference is no longer CC10, it's now standard deviation of CC10, right? Performance goes up 0.191 standard deviations, right? So instead of saying the points of CC10, points of performance, it's now standard deviation of this, standard deviation of that. So now we're comparing something that's a little bit more comparable across things that have different variations. Why I say that is because performance's standard deviation was quite small, right? It was an 18-item test. The scores were 0 through 18, possibly. And usefulness, that thing was like a test that had a mean of 100 or something like that, in a range that went from 50 to 150. But now we can talk about the relative impact of each of these beta weights by saying, okay, for every one standard deviation of CC10, usefulness goes up 0.072 standard deviations. All right, so subtle change in difference, but sometimes we do talk about that. Questions? Yet another thing to compromise. The nice thing is, relatively nice thing, I don't talk about standardized effects in homework. But they do pop up in research from time to time, and that's why I wanted to mention it here. Should we talk about homework? Are you ready? Have any of you looked at it yet? Not up yet. It should be up. Uh-oh. Templin, what did you do wrong this time? I'm sorry you guys have such an imperfect person here. Pardon me? Oh, whoops, my bad. If you go to the homework page, it's up.
No, not the homework page. I was just there, it wasn't on it yet.
So you logged in, didn't see this?
Yeah.
It will be up when I go home tonight. My bad. Let me just talk it over and you can return and relive the magic, shall you? Or better yet, if you want to log into the homework page, here's a tip. Log in with the last name, lowercase s-e-v-e-n, the number 7. And for the ID, use 7 sevens. 1, 2, 3, 4, 5, 6, 7. I have a bunch of blank homework. So you can log in. You should be able to see it. So once again, last name, lowercase 7, spelled out. Password, 777 7777. Okay? Someone's lucky number. Someone's playing craps. So now you can follow this along. This will be up tonight. I'll send you an email. Yet another attempt at humor. Let's go and read this. The data for this assignment were collected within the Department of Cooking Education Sciences at our Midwestern Red State University. The goal of this study was to ascertain the generalizability of a new method of instruction for breakfast construction. That's right. In particular, a sample of 100 participants chose to participate in a 4-week class focused on making better pancakes or making better crepes. At the end of each class, all students were asked to make both dishes. Surprise! In which the dish they had practiced came first and the other was requested as a surprise. A panel of local celebrity judges, I don't know who that would be, then rated each dish on a 1 to 10 scale, in which higher scores are better. The mean rating across judges, the mean rating across all the judges for each dish served as the outcome. Right? So what you have for each person is a rating for how well their pancakes tasted and a rating for how well their crepes tasted. Woo! 2 DVs. Excited? A covariate of the extent to which students had prior experience cooking pancakes or making crepes, whichever class they attended, was also collected, in which 0 equals never, all the way up to 7, where 7 was like 100 more times. Make a lot of crepes, huh? Actually, I did do that when we were doing this homework. I was into like making crepes. I thought that's pretty hard to do, right? So now I've so totally retired. Anyway, Getting hungry yet? Maybe. I don't know. So basically, I'm asking you to do 3 models. You're going to do it in Lavon. You're going to have the mimic equals M plus and estimated equals MLR. The first model is an empty model where you have the 2 DVs in. But remember, you have to put all of your predictors in with a 0 in front of them to make it work. Why I say this is because I created these data. And today I'm checking my homework and I screwed that up. So just remember, like today's class, start with the 0 star in front for the empty model. 0 star in front. If you email me, I'll have an auto reply. Are there zeros out in front? I say that to you in joking because I made these data and I screwed it up. All right? So just remember that. Like, why? I was angry with myself. Why am I not getting the right answer? I looked through everything else. I'm like, oh, yeah. Anyway, pardon me. So then what we're going to do is add the instruction variable in. So we're going to let pancake instruction be the reference group. So crepe class equals 1, pancake class equals 0. I should probably show you my data here. Grab these real quick. The data. There they go. Nope, nope. Come on, Excel. You can do it. There we go. Looks like this. You have 100 observations. Their ID is over here. You have a pancake rating, a crepe rating. You've got whether they're in pancake class or whether they're in crepe class. Use the crepe class one. All right? You have their experience, and then you have their experience multiplied by the crepe class. Because model 2 is just where you put the class in, crepe class. Use that one. And model 3 is where you put experience, class, and their interaction. Okay? So, the initial models will require you to set all the regression coefficients to 0 for all terms not needed. Just remember that as you go forward. But this is designed to get you to not only try to figure out how to estimate these darn models. Another thing you should note is that the cool thing is model 3 is saturated, so it's identical in form to the one we just did in class, almost completely. Model 2 is not saturated, but I'm not making you look at model fit for it. So we just report some results. And then you have a series of questions to answer at the bottom. Some of these questions up here are going to be asking for I'm running out of room. They're like the stupid system that I use that I desperately need to go and switch over to a modern database caps how many characters I can put in these questions, and so they get kind of cryptic after a while. But we'll talk through some of them more. But some of them come directly from the model, like the estimate of the effect of crepe training on making pancakes or making crepes. But some of them that will then want you to form differences between parameters or figure out like this. If you learned how to make pancakes, what's the difference between your predicted value for pancakes versus your predicted value for crepes? Right? If you learn how to make crepes, what's the difference between your ratings in pancakes versus ratings in crepes? So you're going to be eating lots of crepes and pancakes, or at least thinking about it. Anybody going to have crepes? Make them? No. Maybe I should bring my crepe making tools and just start making crepes next week. You can see how bad I am at that too. It's been about 4 years. What? Yeah? Be awesome. And then you see some of the people who are like pros at it, like with the big crepe pans and whatnot. Do we have can we buy them downtown anywhere? Does any shop sell them? Yeah. I don't know of any. Anyway, sorry. That used to be like a thing, and now it's sort of died off. Oh, you can? Oh, wow. Maybe we should have class in the DeBruce Center. All right. So, big picture. Homework is going to be very, very similar to this lecture. So focus on lecture, focus on homework. You have 2 weeks still to do this. Next week's class will be spent largely on this. We will have a quiz between now and then. It's not up yet. I will post the homeworks I swear they're up there. There's just one little flag in the database that didn't get flipped over. But they'll be up very soon, and you'll be able to see that. Anybody want to have questions right now? Okay. One of the reasons why this homework also helps is some people might ask, why would you want to run 2 models at once? And part of the answer to that is for certain comparisons that you may not be able to make when the models are separate. Right? In this case, comparing predicted values between the two for training. That last example I showed you where we constrained the interaction effect to be constant across the 2 models is another reason for it as well. Okay. Well then, no? Yeah. Go have fun. I'll get this posted. I'll spend the extra 10 minutes trying to get this posted, and then we'll go from there. Thank you, everybody, for your time. Yeah, question.
Can you win national championship if you just cancel class?
Oh yeah. Well, I mean, yeah. I mean, tell you what. I'll be here, but you know your attendance isn't needed. I mean, sorry, required. We'd love to have you. You're needed. Just you don't need to be here. I guess what I'm trying to say. And the class. I mean, you're not going to miss anything. I'll have it recorded. I'll be here. I may not be in my best shape if they win, but I'll be here. So, thanks everybody.
Completely separate.